Complex numbers is a nice topic on the paper in the exam. It's both in section 3 or strand 3 and strand 4. For different topics, it's listed in both. I think we've chosen to call it in strand 3 because most of the material for your program is in strand 3. But just imagine for a moment that you have these graphs. We've seen them before. We've seen the quadratic before. Some quadratics come down and they intersect the x-axis twice. They have two real roots. Some of them come down and just touch and only have one root. And some come down and don't touch at all. And they've no intersection root at all. And yet we say, well, we can still solve it. Because we start looking at x equals minus b plus or minus b squared minus 4ac over 2a. And we find that, oh, this part here, the square root part, turns out to be minus something. And we say, how do we deal with the square root of a minus number? Where did this all come from? So what they decided was, a long time ago, they decided that they needed another set of numbers. In fact, I'm going to take 2 minutes just to explain that, just to fit things in context. I know it's late, but I'll seek to stick to time. Just so you know, when you get on the site, the maths.gcd.ie, the first thing I'll do, pretty much within a day or two, I'll certainly have it up by next Monday, is I'll make sure that all the notes on the site are 2013 notes. So you'll see the notes are 2013. So if you're pulling down notes from each of the sections, you know, oh, that's a 2013. Once you start seeing 2013 written on it, like I chose to do on the start of the notes there today, I don't know if you saw it, but you know the header pages, I saw 2013 written on it hard, so that you know it's Project Maths, it's for this year. Same for 2014, by the way. But basically, what I'm going to do in addition to the sessions on the course, there's going to be a few sessions on where we join things together. You might remember this morning that I gave you a joining connection. I call that connections, where you take m as the slope of the line, theta as tan theta, and dy dx, and it's the same thing. There's a whole series of things on your course that are actually heavily locked together, but they're never taught as locked together. So you see them as separate things, which is sort of strange, okay? And when you start seeing them as locked together, you can say, oh, I can come at it this way, or I can come at it that way. So I have a series of other small little pieces I've put up in video called connections. And you're going to see those, okay? And you say, oh, that connects this to that to the other. Like, for example, when you see something like Pythagoras there today, I don't know if you remember Pythagoras, but if we have x and y and z, Pythagoras would tell us that x squared plus y squared is z squared. Is that okay? Now, if, for example, I decided to do something with Pythagoras and say, where else does it come up? Well, this is basically the difference between, if this is y, x2, y2, and this is x1, y1, this distance y is really y2 minus y1. And this distance here is really x2 minus x1. We take the values. Is that okay? And what's the distance between point A and point B? Well, the distance is z, isn't it? But z is x squared plus y squared. But if you wanted z, you'd say it's x squared plus y squared. How do you get rid of a square? Square root, wouldn't you? And you'd call it the positive value of that because it's a length, isn't it? But if x is the distance x, it's really x2 minus x1, isn't it? And if we were to say x2 minus x1 squared plus y2 minus y1 squared, has anybody seen that anywhere lately? That's the distance equation in the line, isn't it? The distance between one and the other. Is that okay? If you were to look at, say, complex numbers, and you were to say, okay, what's the distance between here and here? This is 0, 0, and this is a plus ib. The distance a is the real part, and b is the imaginary part. And the axes are sort of, what are they? They're sort of similar, but they're called real axes, and they're called imaginary axes. Is that okay? What's the distance between this thing? What's that z called? Well, z is called a plus bi, or a plus ib, isn't it? But what's modulus z? What's the modulus of a complex number? Its length from 0, 0, isn't it? And what is it? Well, it's this squared plus this squared. A squared plus b squared, square rooted. It's Pythagoras. And the reason it's b squared and not I is because it's a distance. It's not an imaginary thing. That is a physical distance, b. Okay, it's going in the I direction. So it's b squared, a squared plus b squared. That's the formula for modulus, isn't it? Is that okay? And if we were to go back to this equation, and we were to say that's x and that's y and that's z, okay? And just imagine for a moment that that was the angle A. Leave that there for the moment. What does Pythagoras say? X squared plus y squared is z squared, isn't it? Yeah? Let's say for the crack, I didn't like z squared here. So I divided this side by z squared. Then I'd have to divide this by z squared and this by z squared, wouldn't I? Yeah? Now let's look at that. What is that? X over z squared over squared plus y squared over z is z squared over z squared. Well, I could simplify that. That's really x over z, all squared, plus y over z, all squared, is 1. Isn't that right? And what's x over z? What's x over z for A? What is this? Well, for the angle A, isn't that the opposite? Isn't that the adjacent? Isn't that the hypotenuse? What's x over z? Adjacent over hypotenuse. And what's adjacent over hypotenuse? The cosine, isn't it? And what's y over z? Opposite over hypotenuse? The sine. Effectively, cosine A squared, cos squared A plus sine squared A is 1. Did you ever see that equation? So Pythagoras is everywhere, isn't it? So there's a whole load of connections in all the stuff that we do. That's really quite remarkable. X plus y by x plus y is x squared plus 2xy plus y squared. X plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. Did you ever see a thing called Pascal's triangle? Remember these numbers? Did you ever see that thing? Well, just imagine, I think they give you the wrong question. Instead of doing x plus y squared and giving you x squared plus 2xy plus y squared, what they should do is they should do the calculation b plus g squared. B squared plus 2bg plus g squared. And b plus g cubed is b cubed plus 3b squared g plus 3bg squared plus g cubed. I think people would understand those two an awful lot better than the first one. And the reason I think so is just imagine for a minute that B stood for a boy and that G stood for a girl. Okay? This is a two-child family. B plus G. What does B squared signify? Two boys, isn't it? G squared, two girls. And what's this BG? Boy and a girl. Why is there a 1 here, a 1 here, and a 2 here? If you're going to have two children, there's only one way to have two boys. The boy has to be first, and you have to have a boy second. That's BB. If you've got two girls, and that's what you want, you've got to have the girl first, and another girl second. But if you want one of each, a boy and a girl, you give the boy first and then the girl, or the girl first and then the boy. There's two ways of having that, out of the four possible combinations. Look at it here for three children. Here's a family of three children with three boys. Here's a family with three girls. Three ways of having two boys and a girl. Well, that actually makes sense, because the girl could be first, second, or third. It could be girl, boy, 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 girl, boy, or boy, boy, girl. Here, a boy and two girls. The boy could be first, second, or third. But there's only one way of having three girls. They all have to be girls, or they all have to be boys. 1, 3, 3, 1. So the whole probability is linked into this. Everything is all linked to these equations. Is that okay? And it all comes back. So I'm going to show you those things that we call connections. So look out for them, because when you do see them, you say, oh yeah, I can come at it that way, or whatever. Okay? Now, here we are back on the number line. It's way back in primitive mathematics, and people start counting, and all they know are numbers. I have a fish, I have two fish. I have a bit of cloth, I have two bits of cloth. I have 5 stones. And everything is fine, and all they can think of is addition. And all the numbers add up, and there's nothing other than pure integer numbers. And then somebody says, can I borrow a fish? Could I have some? Could I have two of yours? So I used to have 4, now I have 2. I used to have 5, now I have 3. I have to give some away. Oh, numbers don't add up, they subtract as well. So the notion of having a number that just kept on going indefinitely to east, you had this sort of concept called subtraction. But what would happen if I had 2 fish and somebody borrowed the 2 of them? Then I have no fish. So the concept of having no fish, that never struck them. You either have fish, what's no fish? You have fish or you don't have fish. What would happen if somebody borrowed 3 of them? Minus fish? That would mean that even when you got a fish, it wasn't yours, you have to give it back again. So then they said, we better actually dream up what these minuses are. So they used to have this thing called n for natural numbers, and with the subtraction they realized they needed z as well. And that was okay. And then they said, let's start doing some multiplication. 3 fish times 3 of us have 3 fish each, that's 9 fish. 2 of us have 4 fish each, that's 8 fish. This is great, I'll multiply. But let's say we have to divide the fish we have between 4 of us. What happens then? We have to divide. All right, okay. When you multiply, it's fairly easy. 2 times 3 is 6, it's a number. But 6 divided by 3 is 2. What about 4 divided by 3? Oh. 4 fish, 3 people. What happens there? You get 1.3. 2 fish, 5 people, 0.4. So you ended up numbers between the big numbers, between the integers. And so we better put a number in. We better call these things. So they call these Q. These were rational numbers, things that were in ratios. 4 fish divided by 3 people. That's okay. And there were negatives as well, deaths of fish between people. So they had Q, and that was okay. And then they said, everything's fine. Now let's start doing squares. And everything was fine. So let's square things. 3 fish squared. 3 times 3, 5 times 5. What about taking the square root? And they decided to take the square root of 2. Now, I won't go through it now, but I did it yesterday, so it'll be on the thing. But they found that they couldn't actually get a ratio of A over B, 2 numbers, that was like the square root of 2. It wasn't 5 over 13, it wasn't 15 over 17, it wasn't a ratio. It just didn't work out. There's a proof. It isn't possible to put it in an order like that. No, I don't have time. Okay? So we needed a thing called irrational numbers, and they called them OR. They filled in the gaps even more. And that was okay, until some lunatic decided that if you've got squares, you've got square roots. And what about the square root of a minus number? Or the square root of minus 17? Where are you going here? And they said, come on, this is mad. And they said, well, if you got the square root of minus 17, you actually have to put it some other way. So instead of the number line just being the boring number line, always consider that boring, one-dimensional. You walk this way, you walk back. Never move off the one line. Okay? It's a dreadful diagram. Well, complex numbers, a number could be 2 plus 3i. 2 plus 3i up here. Or 4 plus I. Or minus 2 minus 2i. So numbers actually were from 0, 0, a particular distance. And they said, these are really cool numbers. They're two-dimensional numbers. But there's something really magic about them. When you multiply a number like 2 times 3, it just stays on the number line, it gets bigger. But when you multiply this fella by this fella, what happens is that the numbers rotate. So if this angle here is, say, about 20, and this angle here is 60, if you multiply that number by that number, you end up with an angle of 80. And the size, the modulus times the modulus, gives you a bigger modulus as well. So when you multiply, you actually rotate the numbers. When you divide, because of the way things work in maths, you rotate the other way. You cannot imagine a computer game that doesn't involve rotations. Super Mario, getting bigger, rolling, falling, any possibility. Every single computer game, everywhere, is screaming this stuff, using them all the time. Two-dimensional, three-dimensional space pictures, representing them turning around. That's what complex numbers are for. Cannot survive without them. It's the only thing that causes something to rotate, and rotate the other way. Absolutely beautiful. And the angles add in the multiplication, and the power and the moduluses add. So that's what we're going to do in complex numbers, and that's why it's there. Creates that sort of space. Okay, so let's go through now the notes on complex numbers. I'll just pull them from wherever I put them. Sure, I put them somewhere. I know I was given them, so I have them here. And it's a question of where I put them. I just have to get my sequence right. Okay. Here's my place. Okay, complex number. A complex number is defined as having two parts. A real part and an imaginary part. 5 plus 12i. This part is real. This part is real, the first part, the coefficient, times I. And I is the square root of minus 1. I squared is minus 1. It's given formally as C, the set of complex numbers, is defined as all values a plus bi, where a and b themselves are real numbers. They can be square roots or they can be anything. And I is the square root of minus 1. So here's a picture of an Argon diagram. And it's like the xy, but this is the real axis and this is the imaginary axis. This is the point 7 plus I, 7 out and I up, 12 out, 5 up, 3 out and 4 up. And you can just plot them as points if you wish. Now there's points down here as well and all over, but I'm just looking at that quadrant for the moment. Or you can represent them as an Argon diagram by means of lines, where you say it's a line from 0, 0 to here, 12 plus 5. 12 plus 5 is one of those favourite enough questions in the exam. You know the 3, 4, 5 triangle. Well, the 12 and 5 12 squared is 144. 5 is 25. 144 and 25 is 169. Take the square root, it's 13. So 12, 5, and 13 is another triangle that comes up a bit. So that's your Argon diagram. Now, and if you were to multiply this diagram here, this 7 plus I, by that angle, angle A, and this angle B would give you a total of, for the answer would be up there somewhere, A plus B. It's pretty cool. So here's the Argon diagram then, and it just draws dots. Now it says that if this is the point 2 plus I, 2 plus 2I, the only way you can get there is 2 right and 2 north, or 2 east and 2 north, 2 real and 2 imaginary. No combinations of reals will make an imaginary for you, and no combinations of imaginaries will make a real. These are perpendicular. You can't cross-compensate. So the only way there is to get the two of them to be exactly the same. So they start doing addition then. The addition is 1 plus 3i and 4 plus 2i. How do you add them? That's fine. Just got it right. 1 plus 3i and 4 plus 2i. Add the two together. Well, this is no different than if somebody said the real numbers are bananas and the imaginaries are oranges. 1 banana and 3 oranges, 4 bananas and 2 oranges. Add them up. And like anybody else, you'd put the things in the right piles together. If you come in from Halloween, you put all the sweets in one place. If you got money in another place, all the nuts that you're not going to eat in another place, and all the rotten stuff somewhere else. Is that okay? Maybe bags of crisps somewhere else. And you pack them in all various piles. So you're doing that all the time. So the only thing here in addition is put the bits that are real together, the 1 and the 4, and the 2 bits that are imaginary together as well. So I join them together. The 1 and the 4 come down here. I call them real. And the 3i and the 2i, they're imaginary. And we put I on the top there. Then by linking them, the 2 real bits, the 1 and the 4, go together. And the 3i and the other, they go together. We just add them up. 1 and 4 is 5, or 3i plus 2i is 5. Alternatively, I might have written it here, 1 plus 3i, 4 plus 2i under each other. 4 and 1, 5, 3 and 2, 5. It's no different to apples and bananas. Addition is commutative. It's a very formal term. But basically what they're saying is that if you add 1 plus 3i to 4 plus 2i, it's the same as adding 4 plus 2i and 1 plus 3i. The order doesn't matter. But imagine if this was east and this was north, and somebody said, go out 4 steps east and then 2 north, and then go 1 step east and 3 north. It's the same as going 1 step and 3 north at the beginning, and then 4 and 2 north at the end. So it doesn't really matter which way you go. Do you go, it's like 6 and 2. 6 and 2 is 8. So is 2 and 6. So it doesn't matter what the order is. It's commutative. So that's how we do addition. Doesn't matter, the order doesn't matter to us. Subtraction is the next one then. If Z1 is the complex number 5 plus 5i and Z2 is 1 plus 3i, take one from the other. So again, Z1 minus Z2, I write exactly the same equation out, and I group them into real and imaginaries. Grouping the reals, there's a 5 real there and a 1 real. So 5 minus 1, because I'm taking Z2 from Z1. And on the imaginary, I've got 5, and I've got 3. 5 minus 3. So if I look at that on a subtraction basis, 5 and 5i gives me here 5 plus 5i. If I'm going to take 1 plus 3i from it, it means that one of the steps I went east, or real, I have to take, and 3 of the ones I went north, or imaginary, I have to take. So that brings me down here. I'm taking away 1 and 3. 3 of the imaginary and 1 of the real. And that brings me to 4 plus 2i. Similarly, if I took 4 plus 2i first from it, I'd end up in 1 plus 3i. So it's like 5 minus 3 is 2. 5 minus 2 is 3. Now we get into a nice thing called multiplication. We start looking at how this is going to work. Multiplication, we say 1 plus I times 3 plus I. Okay. It's like the FOIL method in that we've got two numbers here and two numbers here. So if we're going to do that, we'll have to multiply everything in the first box by everything in the second. So 1 plus I times 3 plus I. So using the first one, 1 by 3 is 3. The outsides, 1 by I is I. The insides, I by 3 is 3I. And the last one, I by I is I squared. But there's a rule that says that the I squared thing is defined as minus 1. That's the whole basis of the complex numbers. So you get 3 plus I plus 3I minus 1. Now, this is a real number, and this is a real number. This is imaginary, and this is imaginary. So I grouped them together. Or 3 minus 1 is the real bit, and I plus 3I is the imaginary bit. So the answer turns out to be 2 plus 4I. And that's the answer. So let's see if that makes any sense. Well, they're just numbers, really. And we sort of see it like that. And we say there's 1 plus I, there's 3 plus I, and there's the answer, 2 plus 4I. But if we just saw them as sort of A, B, and C, it's sort of hard to see the pattern, really, between them, because you say it just could land anywhere. But if we start looking at it like this, and we say there's A, and there's B, and here's C, C, we might be able to see now that the A angle, I don't know what it is, but let's call that A. The B angle is quite small, really. And the C angle, then, is the total. And if you were to look at this little space here, that angle there is C minus A. C minus A. And it doesn't look too far off the same sort of shape of pizza or slice as B. So it is working. So there's the multiplication representation, 1, 2, and 3. And we can do it two ways. But on the multiplication of it by the line on it, you can see that there seems to be some sort of association. And the answer, because this was C, this was the 2 plus 4I, this was the 3 plus I, and this was the 1 plus I, the final part, the outcome, seems to be much further over than the other ones. So in other words, it seems to be multiplying that way. It seems to be rotating counterclockwise, anti-clockwise. In fact, one useful way of looking at this, if you think about it for a second, we might go back to the Argon diagram if I haven't written on it too much. Yeah, this isn't bad. Let's imagine if I had the number 5 here. And that's just the point A. The point A is 5, nothing. What would happen if I multiplied 5 plus naught I by I? In other words, 5 plus naught I times naught plus I. In other words, if I multiplied 5 by I, what would I get? 5I. Nothing but 5I. Be up here. In other words, what would have happened is it would have rotated by a full 90 degrees. I multiply by I, and lo and behold, what happens? The whole thing multiplies itself and rotates by this lovely 90 degrees. Look for that other diagram if I can find it. I think it's here. So if I took, say, 2 plus 0I, and I rotated it, this is the point 0, 2I. I rotate again, I multiply I by I, and I get minus, or 2I squared. What's 2I squared? I squared is minus 1. So it's minus 2, nothing. And I go again, down to here, minus 2I, and here, back to 2. So every time I multiply by I rotate by 90. If my favorite number is this stairs that goes up one step up for every one step out, so 1, 1, 2, 2, all the way like that, and I've got 45, a point on this line might be the point, say, 5 plus 5I, or 1 plus 1I. 1 plus I, well, 1 plus I, what do you say the angle would be? Halfway between 0 and 90? Be 45, wouldn't it? So 1 plus I, if that's 1 plus I, it goes out 1 for every I. This is 45. The distance, rather than the I value, because it's mentioned in I's here, that's really the number 1, 1I, because it's a distance of 1. The modulus is 1. So it's 1 plus 1I, because this is the I direction, that's the real direction. The tan of it is 1 over 1. So tan is something that has a tan of 1. It's 45 degrees. In other words, if you multiply anything by 1 plus I, you'll rotate it 45 degrees. Now, in Pythagoras, this would be 1, that would be 1, that would be the square root of 2, wouldn't it? Because 1 squared plus 1 squared would be 2 squared. If I multiply something by 1 plus I will rotate it by 45 degrees, but I'll also multiply its size by the square root of 2. But imagine if I had a triangle that was like this. Nice, neat triangle. Nice, famous 45 degrees on it. But what I'm going to do now is I'm going to call this length here 1. And because this is 45, and this is 45, and this is 90, I can work out the lengths. This is actually 1 over root 2, and this is 1 over root 2. Or 0.7071, 7071. It's the sine or the cosine of that. But effectively this point here is 1 over root 2 plus 1 over root 2 times I. And if you multiplied anything by that number, it would just rotate by 45 degrees, and it wouldn't get any bigger. So Super Mario wouldn't have hit a ping, and he wouldn't have got any larger. He'd have missed it or something. He may have rotated or fallen down. But if he wants to get bigger or show that he's eaten something or shrink back, we may multiply by something different. Is that okay? You get the sort of idea that we're looking at? So all I'm saying is that when we rotate, just like if we multiply anything by 1, it doesn't change. If you multiply something by 2, it gets twice as big. Multiply it by a half, it gets only half the size. If we multiply it by this number, it rotates, but it doesn't actually get bigger. 1 plus I would cause it to rotate, but 1 and 1 would give you the square root of 2. It would be getting bigger as well. Okay, so that was okay, and they got away with the multiplication until there was a bit of a problem. And the problem came with division. How do you divide complex numbers? And they said, before we do that, we're going to do something called complex conjugates. For every complex number, there's another complex number hidden away as its twin, almost like its alter ego or something like that. They go around in pairs. So just imagine this fella here, 3 plus 4i. 3 plus 4i is a complex number. But for every 3 plus 4i, there's a 3 minus 4i. It's almost like the counterbalance. One is hyperactive and one is very shy. Okay? They're both the same age. They're both 3. But this is their mood swings or something. Effectively, if you consider this line here as a mirror, it's like as if this is the reflection of that point in the mirror. In the real number, not in the other, in the real one. Similarly, the point 1 plus I here, or minus 1 plus I, has a twin minus 1 minus I. But there's no reason why the complex number should start on the top one. The complex number could be this point here on the bottom, 3 minus I. But its complex conjugate would be the other side of the mirror, in Alice in Wonderland space, 3 plus I. Or it could have been over here. It could have started here as minus 5 minus 2I. And its image would be 5 minus 5 plus 2i. So there are these two beautiful things going around called complex conjugates. Why are we interested in them? Well, there's something good about them. Here's a complex number 1 plus 2i. And its complex conjugate is 1 minus 2i. I'm going to add them together. 1 plus 2i, 1 minus 2i. What happens is you get 2 plus naught I. The imaginary part disappears. Now, that's not surprising in a way, because really what you're saying in geography sense is you're saying, would you ever go out 1 kilometre east and then 2 north? And after that, would you go 1 kilometre east and 2 south? Well, the 2 north and the 2 south are going to disappear into each other. They're going to go away. But the 2 east, the first east and the second east will continue. Because each time you're adding an east to it. And you ended up here. Another way of looking at it is that the first angle here was a positive angle. Let's say it was about 60 or so. Maybe a bit more. This one here, funny enough, is the same angle, but it's minus. So if I multiply by an angle that's below the line, sure, it's forcing me up. So if this was my first angle and I started here, and then I added this angle to it, well then, sure, that angle is the same as that angle. It would just bring me back to the graph again. Or if I started here, and then added this negative angle to it, it would only bring me up to here. If I multiply complex conjugates together, that's what I was doing in the rotations, that's one angle, and the other angle is all the way back. So when I start adding the angles, this one is forcing me down, it's a negative angle, and this is positive, I end up here at 5. So 1 plus 2i times 1 minus 2i, I'll just do the numbers out loud, or I suppose in full writing here. And I'll say 1 plus 2i times 1 minus 2i is the FOIL method. 1 by 1 is 1. 1 by minus 2 is minus 2i. 2i by that is 2i. And 2i by 2i is 4. I by I is I squared. Plus by minus is minus. So 1 minus 2i plus 2i minus 4i squared. Minus 2i plus 2i is like 2 north, 2 south. I squared is minus 1. By 4 is minus 4. By minus is plus 4. 1 plus 4 is 5. 5 plus naught I. So the multiplication of those two together turned out to be over here. When I did the multiplication of those, I think it might be here. So this is the size of it. This is the size of the second one. And when I ended up with my answer, I ended up over here. How did I end up all the way over there? Why not here or there, or why not 10 miles further on? Well, let's look at what I did. If this is 1 plus 2i, let's do Pythagoras for the moment. That would mean that that's 1 and that's 2. It would mean that that's 1 and that's 2. Now, albeit minuses, but Pythagoras is to do with distance. It's not to do with the direction you're going. So if you have this triangle here, and it says it's 1 and 2, and this is a right angle triangle, what's this length here? Well, can we get it from Pythagoras? 1 squared plus 2 squared is x squared. Okay? That by that by that. 1 plus 4 is x squared. 5 is x squared. Now, how do I find x if I know that x squared is 5? How do I solve for x? Just take the square root, don't I? So basically x, because that'll all go, is the square root of 5. Okay? Now, funny enough, the modulus, or the distance between here and here, is the square root of 5. And because this is a mirror image, this is the square root of 5. And what do we find the length here was? 5. Oh, that's interesting. Square root of 5, square root of 5, 5. It looks like the square root of 5 times the square root of 5 is equal to 5. It looks like the modulus of Z1 by the modulus of Z2 is equal to the modulus of Z1, Z2. One number by another is the modulus of the answer. So when you multiply, if the number itself is more than 1 away from 0, 0 in any direction, you're making this thing bigger. This game is getting in your face. If it's 1, it stays the same. If it's less than 1, it's shrinking. And by 1, I don't mean just 1 in the 1 0, but basically anything in the circle within the range of 1 from 0, 0. Anything in this space here. So that's what the complex numbers are about and the complex conjugates. So they say a number is defined by a plus bi, 3 plus 4i, or anything at all, and its twin is always going to be the same number with the minus before it. Now, if it was 3 minus 4i, its pair would have been 3 plus 4i. In other words, minus in front of the number that was there. Not that it's a negative number, but it's different to the other twin. And they define that with the letter Z bar. So Z bar is the symbol that says that's the complex conjugate, or they say A plus BI with the bar over it. The special thing about these, really cool, is that when you add them together or multiply them, all the messy minuses, all the messy the imaginary numbers disappear. So here we're now going to divide 1 plus 8i by 2 plus 3i. And they say, I don't know how to do this. So what they say is, get that other friend that always helps, get the partner of the one in the bottom here. Let's figure this out. So they say, what's the unlocking key here? 2 plus 3i, 2 minus 3i. Get in there quick. And if you're going to multiply the bottom by 2 minus 3i, you better multiply by the top by 2 minus 3i. So what we do is, when we divide one number by the other, we look at the one on the bottom, because that's the one that's causing us a problem. We don't mind 3 plus 4i on the top, but how do you divide by 3 plus 4i? It's the dividing thing that's the problem. So sort out the thing on the bottom. So 2 plus 3i by 2 minus 3i. So what I'm going to do is I'm going to multiply everything at the bottom by this and everything on the top by this. And I expect, hopefully, that if I multiply the thing on the bottom by its twin, I'm going to get a real number. No imaginary stuff. So 2 plus 3i and 2 minus 3i. So on the top, I'm going to take 1 plus 8i times 2 minus 3i. And that's just the FOIL method. 1 by 2, 1 by minus 3i, 8i by 2, 8i by minus 3i. That's what I'm doing here. 1 by 2, 1 by 3i, 8i by 2, 8i by 3i. So I get 1 by 2 is 2, 1 by minus 3i is minus 3i, 8i in the middle, inside one is 8i by 2, and 8i by 3i, the last one, 8 by 3, 24, 24i squared is minus 1, minus 24i squared. On the bottom, I've got 2 plus 3i by 2 minus 3i. So let's see, 2 by 2 is 4. 2 by 3 is 6i with a minus. 3 by 2 is plus 6i, positive. And 3i by 3 is really minus 9i squared. They cancel. This becomes 4 minus 9i squared. But I squared is minus 1. So it's 4 minus 9 times minus 1, which is 4 plus 9, which is 13. And there's no I, so it's 13 plus not I. So if I go to the next page, and I were to group them all together, the real parts with the other parts and all that stuff, I would get 26 plus 13 over 13, just as I got for the other. 26 divided by 13, 2. 13i divided by 13, 13 elephants divided by 13, just an elephant, just an I. That's our answer. So basically what we're finding is that if we divide here, we end up with the 2 plus I. Graphically, what's happening is that we started off here with 1 plus 8i here. We divided it by 2 plus 3i. And we ended up at 2 plus I. We started with a huge angle, almost 90 degrees. We divided it by this angle here, which is quite a bit, maybe 60 degrees. And we ended up with a little bit left, this angle here. We'll call that angle, say, X. And it looks like it's not far off that angle. It's nothing near the red one, nowhere near the blue, but the blue minus the red, yeah, I reckon they're the same. And they are. So where did this come from then? How do we find out how far a point is from 0, 0? Let's take the point here, 3 plus I. It's 3 out, 1, 2, 3. It's 1 up. And what's that length? Well, it's Pythagoras again. 3 out, 1 up. Standard triangle. Three out, 1 up. Is this a right angle triangle? It is, because it's perfectly perpendicular. The imaginaries can't make up for the other. So 3 squared plus 1 squared is x squared. Or maybe we'll call it z squared because we're in complex numbers. 3 squared plus 1 squared is z squared. 9 plus 1 is z squared. 10 is z squared. Z squared is 10. How do I get rid of a square? Square root of z squared is the square root of 10. The square and the square root disappear, and I get z equals the square root of 10. And that's the definition of the modulus. Or the formula is here, 3 plus I. It's shown here with the bar around it that says get the absolute value. You've seen this before in the number line. It's just saying how far away are we in terms of distance. It's called A plus, this is, every formula is A plus IB. So in this case, this is the 3 plus I1. And the distance is 3 squared plus 1 squared, or the square root of A squared plus B squared. There's no I in there because we're talking about distances. So what do they get you to do in complex numbers? They say simplify something like that. Simplify 3 plus I times 3 by 2I plus I squared. It's nothing different to what you've done before. You just take it one step at a time. Inside you say multiplication first, 3 by 2 because of Pemdas. So that becomes 6I plus I squared. The I squared you do, because it's a power, you do that quickly because of the minus 1. Multiply by the i's in, and you can look at that. I'd just like to leave this question, these two, and then we're done. About 3 minutes, I'd say. Let's say we look at this equation. They say S plus Ti is equal to 1 plus 3I squared. What they're saying is that the left-hand side is equal to the right-hand side. This is an equation. It looks difficult because you say there's S and there's T and there's I. So S plus Ti is equal to 1 plus 3I squared. How do I do that? Well, you do know how to multiply, so let's do that and see where we go. S plus Ti is equal to 1 plus 3I times 1 plus 3I. So that means that that's 1 plus 6I plus 9I squared. That's something like minus 8, I think, plus 6I. Yes. So S plus Ti is equal to that. Now this was very subtle in the first part. It says that if you have a point, 2 plus 2I, the only way to get there is to walk 2 out and 2I up, because you can't compensate. What's happening here? Is this something you think you can solve? It looks a bit weird. But what's the real numbers? They're called, let's say, bananas, and the imaginaries are called oranges. They're just two different categories of things. So if these were categories of oranges and bananas, you'd say S oranges and T bananas is minus 8 oranges and 6 bananas. In other words, you would match the real bits with the real bits and the imaginary bits with the imaginary bits. And you'd say, well, the real bits on this side, that's the S. And S to me looks like it's minus 8 because that's the real bit. The imaginary bit here seems to be the Ti bit and the 6I. So when I look at S and then T and then 6, and that's a plus, and they're I's, they look to me like that's imaginary, and that looks to me as that's real and that's real. And they're equal. And if they're equal, the real bits have to be equal. S has to be equal to minus 8. And T, the imaginary bits, well, they have to be equal. So T becomes 6. So it looks complicated, but actually that was the answer. You just had to map them up. And this, I think, is the pretty well, I'm pushing it, but we're there. We're 5 minutes, we're not bad. An equation, K, W plus W bar is 20, where W is equal to 2 plus 5I. How do you do that? Well, W is 2 plus 5I. Now, this is where you can forget a letter. You need to know your symbols. But what's W bar? W bar is its complex conjugate. Is that okay? The person who goes around with them all the time. The alter ego, the mirror image. So that's 2 minus 5I. So K times W, which is 2 plus 5I, plus W bar 2 minus 5I, is equal to 20. So K times 2 plus 5I plus 2 minus 5I is 20. Let's add up some of these bananas and oranges together. The 2 and the 2, they add up, don't they? So that will give you 4. What about the 5i and the minus 5i? Do they cancel? So if somebody told you that K4 is 20, or that 4K is 20, what would K be? Just divide by 4 on both sides. K is 5. And this is, I think, the last. Well, we'll call this the last, yeah. Okay, the rest we'll watch on telly. X, 1 plus 3i, plus y, 2 minus I, plus 2 plus 3i, is 7 plus 4i. Quite a mouthful. Again, put all the reals together. X is real. That's a real number here. That's a real number. That's a real number, and so is the 7. So x plus 2y plus 2 is 7. And now let's look at the imaginaries. And we get 3xi minus minus yi, y times I, plus 3i equals 4i. But I don't need this I at all stuff. That's the same as writing 3x minus y plus 3 is 4. This is the same as equals 2. Now, can we simplify that? X plus 2y plus 2 is 7. How would we normally write that? Would we get rid of the 2 and move it over? I think we'd call that x plus 2y is 5, would we? What about this here? 3x minus y plus 3 is 4. Would we move the 3 over? And we get 3x minus y is 1. What are they? Have you ever seen anything like that before? They're two simultaneous equations. Is that okay? So all the complex numbers is about finding the roots of a quadratic. If we find the root of z squared minus 6s plus z plus, if we find x squared minus 6x plus 5, and we do the factors, we'll find that it crosses twice. If we do this fella here, x squared minus 6x plus 9 equals 0, we'll find it crosses just once. And if we go for this one here, x squared minus 6x plus 12 equals 0, and we do our minus b on it, we'll actually find that we get complex roots. So I do that, I find the root. We know how to do that. It's az squared plus bz plus c is 0. It's the minus b equation exactly as before. We find the roots, we find the actual where it crosses, and we find that it crosses somewhere out there in imaginary space. So the interesting observation then is if you multiply two complex numbers by each other, here, as we did this one by this one, the answer is that it gets bigger by the size of the modulus and the angles add. If you divide, it does the opposite. So, Shin Shin, thanks a million. Best luck at the leaving cert. And thanks a lot. So safe home and enjoy, okay? Best of luck.